How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And my business today has most uncommon enchantment. And of all the things I like to do, of which there are hundreds in this business of demonstrations, this indeed enchants my soul the most. It has to do with the principle of Bernoulli. Bernoulli. B-E-R-N-O-U-L-L-I. And I urge you to go and read about the Bernoullis, because they were an uncommon family. 120 of them, all geniuses, unlike anything in the history of the humankind. The best that we've ever had are the Bachs in music, and there were only at most 24 of those. But can you imagine over 100 people named Bernoulli, all geniuses, not one an ordinary man? Now I will recite to you quickly and passingly the principles lying herein, these demonstrations, which you can read about in your books. First, we learn from Bernoulli that when a moving fluid like air encounters a constriction, that is a narrow space, the velocity increases. So as we say, the velocity is increased in a constriction. One other principle emerges from a study of Bernoulli, and that is that the pressure in a constriction diminishes or goes down. So we have these two principles. Velocity increases, pressure diminishes in a constriction. And now I'm going to show you an abundance, an array of experiments, demonstrations that reveal this. Consider the following. Why an airplane can fly, says Bernoulli. He explains why. Why a ball can be thrown in a curve. Why a chimney has a good draft. Why a bird can soar. Why a boomerang, whatever it does, boomerangs. All of these things can be accounted for in terms of Bernoulli's principle. Here is a magazine opened so that the pages are curved in this way. And now I'm going to blow a stream of air against the inner edge of these pages. One would think that they would be pushed down by the push of the air. But no, watch. Watch. Well, the page was lifted up. There it is. Now that airplane wing has some flutter, which we don't want, of course, in a real airplane wing. But the air going over the top gave rise to a diminution in pressure, and the atmosphere below lifted the page up. Consider another of the same. Here are two spheres, two croquet balls, with a little separation between them, and this region is a constriction. I'm going to blow some air through there. One would think impulsively that the spheres will be blown apart. No, they are not. The pressure will be reduced and the atmosphere will push them together. Watch it. There they are, pushed together by the greater atmospheric pressure on the outside. Now, of what consequence is this? Well, very important indeed, because if two ships pass, let us say, two ships passing on the sea, if they pass too close to one another, the pressure is reduced between them and they could be made to collide and break apart. Here is another, very dramatic, my chimney effect. Here I have a chimney. You remember a requirement of our work together is imagination. So I could, of course, draw the picture of my house and my chimney, and there's the fireplace in my house. Now, why does my chimney have a good draft? It has a good draft if there is a stout wind blowing across the top of the chimney. Why? Because high velocity, diminution in pressure, the atmospheric pressure pushes the smoke up the chimney. I'm going to prove that. Here is my fireplace. My fireplace is a vessel with some puffed rice. Here is the chimney. I'm going to blow a sharp stream of air across the top. The pressure will be reduced here in this region. The reduction in pressure will be felt in the tube, and the atmosphere will push it up. Watch it. There it is. My chimney has an extraordinarily good draft. Watch it. There it is. I say that's a terrific chimney. Now, here's one that's even better still. Here's a funnel. And I'm going to put some puffed rice in that funnel. And then I'm going to blow some air through that funnel just to show you that air is blowing out of that funnel. Watch it now. Whoop. Oh, well, of course, there it is. Sure, the puffed rice couldn't have come out unless I blew it out. Now I'm going to put a ping pong ball in there. There it is. Now I'm going to blow that ping pong ball out. Watch it. Indeed. Somebody says, oh, he's got it stuck in there by magnets or something. No, no. I will dispose of it as quickly as I can with the following remark. Here it is. Here it is. Here is the funnel. There is the ball. Here is the air. The ball fits in the funnel very snugly, and these regions right here are constrictions, and when the air passes in there, it has a high velocity and a reduction in pressure, and the atmosphere holds the ball up. Indeed, this principle of Bernoulli is why an atomizer works. You know what an atomizer is. An atomizer is a tube that resides in a vessel, and here is some liquid, and here is a tube across here, and here is a bulb, and you squeeze the bulb, air rushes across, there is a reduction in pressure, the atmosphere pushes the liquid up, and then the liquid is caught in the airstream and comes out there. I have often thought that the reason that's called an atomizer is because little atoms of the liquid come out there. Don't you like that idea, little atoms? Now, here is an atomizer, and spray would come out there. Now, I'm going to show you an atomizer on large scale. Watch it. This is fantastic. Here is a tin can, and here is a tube quite like that one residing in the atomizer. And I'm going to blow a stream of air through this tube. There will be a reduction of pressure in the tin can, and now what will the atmosphere do if the can has less pressure inside? The atmosphere will collapse it because it is enormously strong. Watch it. Watch. There it is. There it is. I tell you, that's terrific. It's so terrific, I'm going to do it again with another one. There's another one. Yeah, why? Well, if I like it, I'm going to do it twice. I may do it 3-4 times. Watch it. Oh, look at that. Well, that's 2 times, and I'm going to do it once more. Once more. Why? Because I like it. Watch. Whoop, whoop. Whoop. Oh, well, there it is. Notice, there it is. Wait. There it is. There it is. And I tell you, that's terrific. That's fantastic. Now, pressure reduced in a constriction, velocity increased. Consider a consequence. Flag. United States flag, Australian flag. Why does a flag flutter? Bernoulli. Have you not heard sometimes your Venetian blinds chatter? Bernoulli. The air blowing across the top of the shutter gives rise to a reduction in pressure. The shutter is lifted up. Now, because of its springiness and its inertia, it falls back, and so it oscillates. And I'll tell you how powerful an instrument Bernoulli's principle is. Some years ago, a bridge way up in northern Washington collapsed because of the effect of Bernoulli's principle, because of the role Bernoulli played. Now we got something wonderful. Terrific. Oh, why is it terrific? Because you would not believe it. Here it is. Supposing I had a tube, and I drove a stream of air up here, and I had a ball right at the top, vertically above the blowing air. You would say if the ball stays there, it's because the air pushes up and the ball pushes down, and when they are equal, the ball stays there. And that would be correct. But now supposing I turned the tube off the vertical and the ball still stayed there. Well, you can't say that anymore because when the ball receives the air that way, there is a component that way and a component that way. That one may hold up the ball, but this one should drive it away. But I'm going to show you that it doesn't. Watch it. Up, up. Little trouble. Uh-oh. Let me try a heavier ball, a golf ball. And I call to your attention a very significant feature of this. The ball was spinning. This spin gave rise to a reduction of pressure on the upper side, whereupon the atmosphere held it up. Let's take a big one like this. Styrofoam ball. Watch it. I hope we have air enough. Watch. And I say that's terrific. I just love that. I want to do it again because I do. Any objections notwithstanding. Question, could I get that ball on the horizontal? That's a good one to explore. Indeed, you can do this by going to your gasoline station and using the air hose at your service station. Let me do it again with a golf ball, which is quite heavy. Golf ball, quite heavy. Oops, little trouble. Now, finally, since I enjoy, as you know, the physics in toys, here is a wonderful demonstration of Bernoulli. Here is a little toy car. Here is a little toy car. And what am I doing? I am storing some energy in a wound-up spring, and when I release the spring, it unwinds and turns a fan, and there is a stream of air emerging from here. I'm going to show you that there is. Watch it. There's a little polystyrene ball. There it is. Now remember, I can put that off the vertical. Watch it. There it is. Now what I'm going to do should be an enchantment for ages 4 to 94, as all the physics that we do should be. Watch it now. Watch. Oh, isn't that something? Look at that. I want to do that again because I like it. There it is. This is a Bernoulli car, and why does it work as it does? Because, one, there is a push of the air, a high velocity on one side of the ball, which gives rise to a diminution in pressure, and thereby the atmospheric below holds it up. Now, what shall we say about Bernoulli? The applications are phenomenal. As I've remarked, two ships passing on the sea should not pass too close to each other. Indeed, have you not stood on the sidewalk when a fast-moving vehicle has gone by and you have been made to rock? Or have you not passed in your car, a bus, let us say, and your car is made to rock? This is a consequence of the reduction in pressure between the vehicles, whereupon the atmosphere on the outside pushes them together. Indeed, when the Japanese designed their most recently accomplished railroad from Osaka to Tokyo, where the trains go about 120 miles an hour, what was the critical thing? Several. One, the center of gravity idea. Number two, how close can the cars be without the effect of Bernoulli? And so I say, read about the Bernoullis. They are wonderful to know about. And I thank you for your attention.